Okay, cool. So now moving up next to fixed spanning sets. So we started with the hypothesis. So the hypothesis is made for mathematical simplicity. And the hypothesis is that the data is mean centered, okay, which implies that the mean has been subtracted from each original sample. So the data samples are centered at 0. So we will see 3 quick cases here. So perfect representation using a fixed spanning set. So this is unsupervised learning. Okay, so unsupervised learning includes PCA, dimensionality reduction, K-means, clustering, also factorization or matrix completion. So we're moving basically from the supervised left side of this map, right? So all of this is supervised for now. And we're gonna talk about how to formalize unsupervised learning problems as, learning or defining spanning sets for representing data. All right, defining spaces, new subspaces where we can represent data better. So the first one here, so we can learn how to represent a particular data point, xi, okay, using what we call a new basis of spanning vectors. So this is how we define, representation, okay? So basically, let's start from the beginning. So we have xi, each point xi, which is a sample right here. Xi is d-dimensional sample in this case. We have d features. Will be represented using a weight vector that has k values. So these are the coordinates. So if I write them down, these are the coordinates of my point xi. The coordinates where? In my subspace C. So C actually is a spanning matrix that has k spanning vectors or bases. C1 is the vector 1, C2 vector 2, etc. until you get to CK. And this is, my spanning vectors, okay? So now when we say fixed, it means the C is predefined. It's a prior data. So I do have my C. I define my C matrix. And when we say perfect, perfect means K is the same number as the original features, okay? So we have K equals to D in this case, right? So it's a perfect representation using a fixed spanning set. So somehow you define your C, you define it the way you want, you put a bunch of values, right? And then you have your first C1, your C2, etc. And you say, look, I am defining my space the way I want to define it. It's a prior space. And all that I want to do through this, equation is to learn the WI, the new coordinates of my point XI into this new space C. So what is happening with this, perfect representation? So you can think about it as a change of basis. So when we try to learn the representation W1 to Wn for every single sample, so N is the number of samples, okay? So we're gonna learn a coordinate vector, right? For every single sample. So here for sample I, right, as I mentioned, this is for sample I, but later on we'll try to optimize this for every single sample. And what is actually doing, think about it, guys. What is it actually doing if you think about it? It's taking the original space, so let's put it in blue. This is the original space, my d-dimensional space, okay? Where we have, dimension 1, 2, 3, and this, my x point I belongs to this space. So when I define another space, I say, this is my new space. And what I want to represent a point right here in this kind of new space. So how am I going to do that? How am I going to do that is by learning basically a W that allows me to map this point, W1, Wi for every point, okay, into this space, and maybe I'll find it right now, right here. So these are the new coordinates of my point. So this is exactly what it's doing. It's changing the basis. You go from, base 1 to base 2, and it's a perfect representation into a new space. All right. So this is, how we formalize it. So basically we have an equality here, which means, you can, because you have the same number of dimensions, you can have a perfect representation of your sample into the new space. Okay, so you go from first space to the mapped or transformed space. Okay, cool. So now next, so here, if we look at this, so if you guys, we just multiply simply by the C transpose trick. So it's also mentioned in the lecture. So if you do a simple multiplication by a C transpose here, so you take this first, this matrix right here, this equation, and you just simply multiply by CT, left multiply, okay, C transpose. So it's the transpose of the basis. So if C belongs to RD times K, C transpose will belong to R K times D, okay? So now what we have right here, the idea is that in the new space, okay, so we have basically so what we call WI star is the optimal one, is called the encoding of the data. So this is, the encoding. And then when we multiply it by C, we actually decode it by the new basis. So in this case, right, so this vector right here in this simple representation, we call it the encoding of sample xi, okay, which is wi. And then when we multiply it back somehow, we decode it into this new space. So what happens here is that I have an original point over here in my new space, in my original space, sorry. So this is my original point. And then, so basically this original point has two coordinates, x small, let's call them 1 and so this is my first point, let's call it point I, just for the sake of simplicity, coordinate 1, xy 2, coordinate 2. And if I want to, represent it in a new space, so let's say this is my new space right here, okay? And it happens that now I'm representing right like this. So this new space has C1 and C2. So these are the C1 and C2. And now if I want to represent my point as a new space, you see it's the origin. So it will be right here. So this is actually the coordinates right here, which are the encoding into my space, are W1 and W. So W1, 1, because that's point WI1, so that's point I, sorry. So let's keep it generic. Okay, this is point I, and WI2. So these are the encodings or the coordinates of my point in the new space. And when I actually represent it here, it's called that I have decoded it into this space, okay? So now let's move up next. So we have seen the perfect representation of fixed spanning set. What if the spanning set is actually orthonormal? Orthonormal, it means orthogonal. So here it presents a better solution because we can calculate the W right away. So let's see how we do that. So first we have CI, the norm is equal to 1 because it's orthonormal, right? Unitary vectors. And when you project each a basis vector CI onto CJ, they are orthonormal, which means now we have orthogonality between CI and any CJ in the database for I different from J, all right? So it happens that when you have an orthonormal basis or spanning vector matrix, this is how we define an orthogonal matrix. A matrix is orthogonal when you do, the basis of the matrix is orthogonal when you have C transpose C equals to identity matrix, here D times D. So here what happens if we take this equation, right, and then we replace C transpose C by identity, we're going to get a beautiful expression of our optimal WI star. So WI star is actually C transpose right here, you guys can see it. It's C transpose times XI by just substituting this, orthogonality condition that we added, this constraint that we added to our spanning set. So now basically, if you go from a very messed up space, let's say like a space where you don't have any orthogonality, you have D dimensions, you can re-represent the data, transform the features of a point xi, all these D features, transform them onto a space. So it's still perfect here. So we still K is equal to D, into a space where things become orthonormal, okay, orthogonal, the basis, okay? So we call this Wi, as I said, the encoding of xi through the matrix here, C transpose. And if we take the original mathematical formula of the representation that we have, so we have CWI basically equals to xi. So the decoding of wi, so we have xi decoded. So this is actually wi, this part. So this first part is actually the encoding. So here we encode xi using a C transpose, okay? And then the second part, we actually decode this wi, which is this term, right, into xi. So this is what we call an autoencoder formula. So C transpose xi. So if you look at it from far away, what we have C transpose xi equals to xi, which means this function right here is self-encoding the same feature vector or the same sample. So this is the autoencoder formula. So xi is first encoded, into wi via C transpose, and then decoded back to itself via C. Okay, so here via actually, let's write it CT into. So CT is actually the encoding function, and then this is the decoding function over there in a generic way. So the encoding transformation and the decoding transformation are inverse operations in this case because we have orthogonality. If we didn't have orthogonality, they would not be inverses. All right, cool. Now we have seen different examples. So perfect representation, we're still using a fixed set, which means our target space is defined. The last one is when we have imperfect representation using a fixed spanning set. So here basically, because in this case, when we have imperfect, it means the K, the new space is smaller than the original space. So I'm taking my original vector that has D features and I'm mapping it onto a space where I have only K features. So I'm reducing the dimensionality. And you may ask why we need to do that. So there are so many reasons. First, as I mentioned before, and this, you guys, I think in lecture 10 of machine learning, like the machine learning blinks, we talk about dimensionality reduction and how, not all features are important. So if you want to classify a dog or a cat, there are so many background pixels like in the image that will not tell you if this is a dog or a cat. So ideally, you would learn how to extract a very good representation of your sample in a new space that allows you to easily, classify dogs and cats. So it kind of groups them together, and this representation is very efficient, and it captures what distinguishes, what is unique about the data, I would say, and distinguishes classes at the same time. So in imperfect representation, we only hope to approximate the data set. So we are not transforming the data. You guys got that. So we're not just mapping from 3-dimensional into 3-dimensional. Now we're mapping from 3-dimensional into 1-dimensional or 2-dimensional. So we're losing information. So we can no longer perfectly represent every possible point in the input space, okay? So especially in this new space that we are creating. Also, we reduce the dimension of the spanning subspace. So each encoded point will be represented in a lower dimensional space by a fewer coordinates, as I mentioned, K coordinates. And then we may lose some information about the original data during the reconstruction or decoding task back to the original space. So let's look at this example here. So this is basically the autoencoder process, and you can see that ideally we would have a self-reconstruction, right? But now we don't have equality anymore. We don't have equality because K is smaller than D. And it's the same problem. So what we have here, guys, look, it's beautiful. We have the C matrix, that's our new basis, right? And it may not be orthogonal, so we don't have this equal to identity necessarily. So this is generic, but we do have an imperfect representation. So now we're going to multiply C by C transpose. So this is the C transpose right here, right? The matrix. So we transpose the matrix. So if we have D times K, the transpose will have K times D. And then we have one single sample. So we want to represent this sample, which is D times 1, right? So what happens is that this whole block right here, which is, C transpose Xi, C transpose Xi. This part is called the encoding of the data. So here we encoded the data. That's the encoding. And this is what we called earlier the Wi. All right, so that's the encoding. So first we encode sample Xi, okay, into the new space using C transpose. And then after we encode it, what do we do, guys? We simply decode it using C. So when we do C, times Wi, so this part is the decoding, as I mentioned earlier. So let's see the loss of information. You can see it clearly here. It's a beautiful illustration from the Machine Learning Refined textbook by Jeremy Watt. So this textbook is priceless. It has a lot of nice illustrations. And then now here what we have. So first we have our original data. So the original data lives in a 3-dimensional space. Now we defined a new space spanned by C1, C2. So C1, C2 are these vectors. C1, C2. So when we project the data, when we encode the data into the new space, what happens here? So we are actually getting the P vector, okay? So here's the WP, the encoding. So it depends. So here we have only one value, right, of XP. So actually two values because two coordinates. So this is, these are the new coordinates, WP1. So we can do it like this, WP1, WP2, P is a point, and we have encoded XP, right? So into, like we represented XP using WP. So this is actually C, what do we call it? C transpose. So C transpose XP is equal to WP, which is the new representation or the new encoding of XP in this new space. And it's a 2-dimensional space, okay? So everything now, all these points are represented in this new dimensional space. Now, what happens when we decode, guys? So this is very important. So when we decode, okay, we need to multiply WP by C. So this is the decoding. So this is our WI here, for example. Okay, so we multiply it by C. So we're projecting somehow back into this space. So when you guys project back into the space, what happens now, all decoded points are represented into this new, into the original space. We are back to the original space when we decode, but somehow, right, the decoding lies onto, it is represented in the 3D, but it's still, somehow a compact form. Everybody belongs to the same hyperplane because of the dimensionality reduction in the encoding space. So what happens here when we decode, we actually drop XP perpendicularly onto the subspace spanned by C. So this is what happens. We drop here perpendicular. Okay, so all these points are dropped onto the new subspace spanned by C1, C2. And when dropping that back, you guys can see we're making a lot of mistakes, right? So here, these distances are actually mistakes because now my points are kind of cramped into a lower dimensional space. All right. So I hope that you guys get clearly the concept of encoding using CT, decoding using C of what has been encoded back to the original space. And it's something very important to understand that when you decode, you always decode the data back to the original one. Very cool. So now we get to the very last part. And we talked here so far, we talked about fixed spanning sets, which means the spanning set is actually predefined, right? Now we're going to make it learnable. So why learnable? Because you don't know which space will best represent your data. So ideally, you would learn the spanning set, the new space that enables you to better represent the data. And learnable spanning sets can be formalized, all of them, as matrix factorization problems. Okay, cool. So I think what we're gonna do, let's take also another 5-minute break, and it's also a good break for me. Okay, guys, and then we're gonna come back with this, quick summary over these, like 1, 2, 3, 4, 5 examples, and then move on to the next part. Okay, so let's have a 5-minute break. Any questions so far about this? Is this clear? Kana? So building on what we have seen earlier, we will look at different examples where we have now a learning spanning sets, and these are conventional and supervised machine learning examples where we're trying to learn a good representation of the data for dimensionality reduction or for K-means. So what we have seen before is that like the linear autoencoder formula can be formalized as problem can be formalized as minimization of a first term where we encode and decode the original sample and basically reconstruct it back. And the goal is to minimize the distance between the decoded sample that we encoded, right? So the decoded representation and the ground truth one. So that's our goal. And that's why we have a loss function that minimizes over the set C. So now we have formalized this as a minimization problem, which means we are trying to learn the set C. So we're minimizing over C, and this is the variable of the loss. And we will see later on that, we can derive the loss with respect to matrix C and set it to 0 to get the optimum of this loss. And this will be our C star, the optimal C, right? So when solving this, we have seen in a lecture, if I remember well, Machine Learning Refined. If you guys haven't watched it, you can watch it on YouTube, on how to actually calculate the solution of this optimization problem. And if you look at that, we will discover that the solution of the linear autoencoder is actually the principal components. And these principal components, they point in the dataset largest direction of orthogonal variance. So the dataset varies a lot. If you look at the spectrum of the data here, the variability is carried away by this axis. So that's the maximum variance of the data. So if you project the data, you will see that this is, a maximum variance. That's, like call it length of length delta. But if you project the data onto this axis, for example, you will see that it will kind of, it will blend into this kind of segment, and this segment delta, that's called prime, is actually smaller so than delta, than the first blue delta. So basically, this is not the maximum variance. So when you do PCA, you actually learn a space, a spanning set, and that spanning set of your linear subspace is maximizes the variance of the data. So we're going to have PC1 here. So that's the first spanning, for example, vector of my C matrix. And if I have only 2 PCs, so I'm going to have PC1 and PC2, and this will be my C matrix, okay? So this is what we would discover. And additionally to that, actually C is orthonormal, which means the C that minimizes L, the loss function is orthonormal, and it is given by the eigenvectors of the data covariance matrix. And this is what we discover through the whole optimization process, step by step. We discover that these PC1s and PC2s, the new spanning set of my new space, right? So PC1 and PC2 actually are the eigenvectors of the data covariance matrix. So if you look at, if we project the data onto this new space right here, so you can see this is a new space, right? And we rotate it, so you have C1 and C2. This is how the data, the encoded data looks like in this two-dimensional new space. And if we look at this, how do we get that? What is C1 and C2? C1 and C2, actually, it's the eigenvectors of the covariance matrix. How do we get the covariance matrix, guys? So first, if you remember, this should be something that you'll always remember, should not forget. So a covariance matrix, when you have X matrix, D times N, so N is the number of samples, D is the number of features, you calculate the data covariance by taking XX transpose, right? And dividing by the number of samples for normalization right here. So that's the data covariance. And the dimensionality of the data covariance, depends on the number of features, and it does not depend on the number of samples. So it should be D by D. And why it is D by D? So actually the feature, so we can also see it mathematically, but we call it the covariance matrix because it has covariate. So each element here is a covariate, and the covariate is actually the features of the data. So we want to know feature I, how does it covary in distribution across all samples, okay? With respect to feature J. So we have the distribution of feature J and the distribution of feature I, and we want to see their covariance, their relationship. And this is all encoded beautifully in this compact multiplication of the matrix and its transpose. And I think in lecture also 3, I go in detail, I'll go over this in detail and explain how do we actually calculate the covariate value inside and what it means, etc. All right, cool. So now when you do an eigen decomposition, and also eigen decomposition is very known in linear algebra. So when you take a matrix and you perform an eigen decomposition of the matrix, you kind of decompose it into multiplication of a matrix V that has orthogonal eigenvectors times the eigenvalues, which are the coordinates, and times, again, the transpose of V. And this is the eigen decomposition of a particular matrix. And our input matrix here is actually the data covariance matrix, okay? So the case where PCA fails, if we think about it, so PCA works in a space where the data variance, we try to find the orthogonal spanning set that maximizes the data variance. But what if we have the data set lying in completely different spaces, so subspaces? So you have the first distribution looks like this, right? And then the second distribution looks like that. So you can see that actually the data lives in completely two different subspaces. So if I try to maximize the variance, PCI will completely fail because it will look at this as a whole data set and will try to kind of find the directionality that maximizes this. So maybe it's this directionality. So this one will not actually represent the data well. Why? Because when you project the data, you project it onto this segment, right? And you project the other samples. And if you want to classify, right, if these are completely different subspaces and they are completely different objects, you have a big overlap here. So PCA actually fails when the data points, they do not live in a single linear subspace. So they're scattered across multiple subspaces or hyperplanes in a high dimensional space. All right, cool. So we have done that remark also during the lecture, and now we move to the second example, which is also a matrix factorization in a spanning set learning example. So we can look at K-means, which is a simple clustering algorithm. So I'm gonna remove this just for the sake of simplicity. Okay, so K-means, basically we have a bunch of points, endpoints, and we want to discover the cluster centroid. So we want to cluster the points into different clusters or groups based on their similarity. So similar points will be clustered together, and we will identify the centroid, the center of each of those clusters. So if, you know, this point belongs to the green cluster, it should be closer to the green centroid, right, compared to others. Should be far away from the other centroids, right, because it belongs to the green cluster, and this applies to all other samples. So basically what we want is we want to identify, ideally, to learn this, you know, CK, the centroid, and this is the centroid of cluster K. So K is the cluster, and here we have a set of points. So SK. So SK is the points, is a set of points I, training points I. If xi belongs to the kth cluster, so it will give you the index of the point that belongs to the cluster. So for example, this point xi is equal to 200. So, you know, like, so S basically for cluster, let's call it 1, it has the index 200 plus the index, for example, 2, plus the index of this point 3, for example. Okay, so that's what it means, basically. It's the indices of the points that belong to cluster K. And now if we move forward, so we can formalize this as a minimization problem. So what we want, actually, we want to identify the CK. So we're optimizing over these. So we want to identify the points that minimize, you know, the distance to all points belonging to that cluster. So this can be formalized as a constrained matrix factorization problem. So let's see what is the constraint here. So if we look at this example, so we have a matrix factorization problem where we define our loss function. We have two matrices, C and W, and we want to estimate C and W, both matrices. And the loss is actually the Frobenius distance between our original data matrix, X, right? And the multiplication, the factor matrices C and W. So we want to factorize X into C and W. And if you think about it, maybe you have never thought about clustering as a factorization problem, which is like here, it's like very interesting because look, we have our data matrix X. Okay, so these are all my points. These are all my original points, by the way. So this is the data. And then X belongs to D times N, D number of features, N samples. So we have N samples. So D times N samples. And what we want to do, we want to represent each sample here as a multiplication or as into a new space spanned by C centroids. So if we have C centroids, first centroid, okay? So let's choose a different color maybe to represent this. Okay, so we have centroid 1, centroid 2, centroid 3. So C here defines my new space. Okay, so this is my new space. And we have seen this, by the way, guys, in the deep matrix factorization earlier. So we have a new space that has D features and K bases. K is the number of clusters. So ideally, these new bases will define the centroids, the centers of each cluster. So of course, in the beginning, maybe I don't have the center if I optimize. So this would be any of these points, right? So during the optimization, I'm going to start with wrong guesses and then until I get the perfect centroid. And once I learn C, which is the C hat, it's what it is learnable. So that's why it's almost equal here, right? So we learn the C hat and the C and the W hat. We can easily reconstruct the point. So this point xi will be a representation of these three times we take the wi. So wi, so let's say this is the column wi, all right? So these are the coordinates of these points. And when I reconstruct the point, I can see that this point right here belongs to the red cluster because it has one there. So basically when you perform you know, the multiplication row by column, you will set all these values to 0. You guys can see, and all of these will remain the same. So you're picking up the center. So somehow, you know, this xi becomes the centroid, like you transforming it, you're mapping it into itself. So using this, you know, kind of, you know, like basis of vectors. So this is the idea. where you're representing each point as a linear combination, but it's a very strict linear combination of multiple centroids or vectors, right here of the basis that we have. So the problem with this WI is that it's very restrictive, right? This is what we call hard assignment. It's the assignment matrix, okay? So hard assignment means that we have either 0 or 1, which means here WI, so this is the constraint such that it's a constraint optimization. WI belongs to EK, and here it means that, you know, the WI is equal to EK for, you know, where EK is equal to 1. So which means here, if I have the position K, the entry K in my vector, everybody will be set to 0, except this value, the kth value will be set to 1, which means this point will belong only to one of these centroids. So that's why it cannot belong to multiple. It will belong to only one cluster. And that's the key idea of adding this hard constraint. So if you want to soften this constraint, you can have more like kind of, you know, floating values. So you can have, for example, here, instead of having 0, 1, 0, you can have, for example, 0.1, 0.8, a peak at the green class for this centroid, the second centroid, and then 0.1. So the summation is 1, right? So you express this vector as a linear combination of these 3 vectors right here, and this gives you the coordinates of the point in this space. So it's beautiful. You guys can see it. The space is like C1, centroid 1, you know, C2, and the third one is actually C3. And then if the point belongs to C1, so you'll see everybody will be at the same point right here. So this is, you know, for example, XI, okay? All right, so that's that. So this is a constraint optimization, and clustering can be formalized as that. Now we have seen something so interesting also. We have seen that sparse coding is a generalized clustering. So sparse coding, it means we have sparsity. Sparsity, if you guys don't know what sparsity is, means that, you know, the majority of the values, if I have a matrix A, majority of elements in A are almost equal to 0. So more than, for example, 95%. So I have a lot of 0. So my matrix is sparse, okay? So sparse coding is considered as a constraint matrix factorization tool that generalizes K-means, where data points can belong to multiple clusters. So that's a very nice kind of constraint, which means we have overlapping clusters right now. So for example, if I have this, you know, first cluster and I have this second cluster, right? Now what happens is that I have my first cluster, right, like this, and I have my second cluster like that. And this point right here, it belongs to both, right? So it should actually belong to the centroid of the pink cluster and the centroid of the green cluster. So how are we going to do that? So if we take my point XI, and I want it to belong mostly to the centroid of the green cluster, G, and the pink cluster, P. So these are the indices, right? And I take the coordinates of my point, the coordinates, the weights of my coordinates in this space. So I should have maybe 0 over there, or 0.1 small. And then I'll have a peak here, 0.8, lots of zeros, 0.9, and lots of zeros. And this is what it means. It means that actually the point belongs to these 2 clusters because it has a high value over there, but the remaining values are almost set to 0. And this is why we call it a sparse W. So W here, the assignment matrix that we have now to different centroids or different cluster is sparse. It has lots of zeros, all right? So this is also could be beautifully written into these, you know, optimization problems. So we minimize over CW, and it's the same optimization, same loss function that we defined here, very simple, but we add a constraint subject to the norm of W, the L0 norm. This is called the L0 in sparsity. L0 norm of W is smaller than S. So what is L0? L0 basically of WI, so this is, you know, these are the coordinates right here. So I have many, many W's here. This is my WR, which are the coordinates of the point XI that I showed over there. And it's the number of non-zero entries. So how many non-zero entries here? How many non-zero entries I have here? If I put all the rest to zero, it's very hard. So if I have 2 non-zero entries, right? So 2, it means I have 2 centroids. So 2 clusters, sorry, that my point XI will be assigned to, the pink and the green. So S here, the constraint S, is actually the utmost number of clusters that a point can belong to. So if I set S to 2, it means one point is allowed to belong only to 2 clusters. If I set S to 3, it means I can allow another value here to be very high. So maybe I can have a 0.9 here, and this will be a 3rd cluster over there. Okay, so which means my point will belong to this 3rd cluster. So this is what it means right here. Okay, guys, so sparse coding is actually a generalized version of clustering, and it could also be formalized as a matrix factorization problem. And it's also about learning what? Learning a new representation space C, where when I represent my samples, I can assign them to a single, like basically I can discover their weights with respect to centroids. Okay, so centroids or the clusters that I have. So it's also about learning a subspace or a new spanning set. Now, just to summarize, all of these could be, our generalized, matrix factorization. A particular case that we have seen is also what we call non-negative, which means, you factorize the matrix where you try to find a spanning set to represent only positive data. So X is positive, which means C and W should be positive. So we have the constraint subject to C and W matrices are positive. So if we look at the original, if we write these down, so we have the original matrix X, which is D by N, is factorized into 2 factor matrices, C of dimension C times K. K is the number of, the vectors, the spanning vectors in the new subspace. And K times N is actually the weight matrix of, the new coordinates, the new representation of my, points X into the new space C. Okay, so the new weights or the new coordinates. All right, cool. So to summarize, all of these problems can be regarded as matrix factorization. So with different constraints on C and W. So principal component analysis, C should be orthonormal. So because it's a linear autoencoder. Recommender systems, we have seen this before. So there was no constraint, but X is actually only partially known. So this we have seen this in the previous lecture. K means clustering. Each column of W is standard basis vector, which means standard basis should be like 0, 1, and then other 0, or 1, all zeros, 0, 1, zeros, etc. All right. Sparse dictionary learning or sparse learning is also, we impose sparsity over W. Non-negative matrix factorization, C and W are non-negative. And this is taken from a paper by Flanner in 2017. It's called A Deep Non-Negative Matrix Factorization Neural Network, right? So the reference will be also provided, and you guys can read more about these different examples. All right, cool. Now, one last step to kind of wrap up this map is the generalizability of matrix factorization to multiple layers, and this connects deeply to deep learning. So deep learning can be formalized as a deep matrix factorization or deep representation learning of an original data X. All right, cool. So now let's look at this together right here. So in this example, we have the original, as I mentioned. So we have the original decomposition. So X0 is decomposed into A0 and S0, right? But then S0, which is the assignment matrix, we decompose it into new a new matrix factorization problem. So we factorize recursively. We factorize S0 into a new, into two matrices, and then we take basically the S1, we factorize it again into A2, S2, etc. And we keep on doing this until we get, all of these vectors right here, all of these, spanning spaces. And these spanning, excuse me. These spanning spaces right here, they allow us to kind of, as I mentioned in the past lecture, that this is a projection of different subspaces. So you go from the first subspace, right, into the second one, smaller one, and then into another one. And you're kind of mapping a coordinate space, like a 60-dimensional space into a 30-dimensional space, and you're projecting and mapping the 30-dimensional into 20-dimensional space until you get a very small space. And this very small space, the final matrix, the final weight matrix, will represent the data. These are the coordinates of the data into this very final composed space, right? So it's the new final space. So this matrix represents, this huge matrix represents the new space with maybe 4 dimensions. And here you're going to have the coordinates of my point, which has my original point, which has only 4 values. Okay, so these are the 4 weights of the coordinates of my point in this space. And you guys can see we have seen this before. So basically, we have this beautiful decomposition. The first matrix A0 represents the spanning set of the first layer, right? And then we have the second matrix is the spanning set of the second layer. And the L matrix is the spanning set of the Lth layer, until we get the final S right here, which is also the coordinates of the samples in the very final representation layer, okay? Cool. So if you guys wanna learn more about this, you can also watch the previous video on matrix factorization and how we decompose them into sub-blocks, and we keep on decomposing, and how this connects beautifully to deep learning, because actually this linear algebra and algebraic formalization can be translated into a computation graph like this, where you have, for each sample that has here in this case n features, each sample plus the bias can be represented as, into different layers, mapped into different layers through this, consecutive decomposition, hierarchical decomposition. And in this case, you guys can see that the goal is actually to minimize this simple L2 norm, right? Which is a matrix factorization with the following constraint. We want that A cross X, we want it to be equal to S. So which means we are decomposing each S onto this, a pseudo inverse actually. So the A cross is a pseudo inverse of X. So we're just, kind of setting, the idea is very simple. X is equal to AS. And then if you want to decompose S, right? So again, which we have done right here, right? You need to have somehow multiply by the inverse. So I'm going to multiply by the inverse of AX, and then this will nullify, and then this is what we're after. So every time we keep on decomposing in a deep way, and sometimes A will not be invertible. So if A is not invertible, we will use what we call the Moore-Penrose pseudo-inverse of A. So if you cannot invert A, right, you can use a pseudo-inverse, and this is commonly used. So the pseudo-inverse has a beautiful, compact algebraic formula, which is A transpose A, and then you take the inverse of that, and then A transpose. Okay, so keep that in mind, because if you cannot invert matrices, you have some errors, you can always use a pseudo-inverse and have beautiful solutions to your problem. So here you guys can see in this linear network what we actually have. We have, we're mapping using A0, S0 layer, that's the first layer, and then A1, S1 layer, next layer, and then until we get to the third layer, which is here, they start with the index 0. So it's like that's kind of 1, 2, 3. All right. Cool. So this is, deep non-negative matrix factorization, and this has been presented in the detailed in the paper that I mentioned earlier. Very cool. So you can see that deep learning actually learning these weights right here, right? Somehow. And in this case, we kind of are, we can change the number of these, of course, to different dimensions. So here it's set to T, but we can change those. We can vary them across different layers, of course. But the goal of this is to learn these weights, to learn the A, and to actually learn the S. So we are learning two things here, guys. We're learning the A, we're learning these connections, these weights right here, that like, you know, the mapping, the transformation matrix of the space, and we're learning the representation or the weights in the new space. So these are kind of, you know, all of these are learnable, right? So that's that. So you're learning the new space and the representation in the new space, and this is what deep learning is doing. Great. So I hope that now we can see clearly the power of matrix factorization and its link to unsupervised learning, also deep learning. And we can, by the way, use it for fully supervised tasks and semi-supervised tasks. So we'll see different examples also in the future.